In this video, we're going to answer some questions related to heat of solution and heat of dilution. So let's get started. Define the following terms: enthalpy of solution, heat of hydration, lattice energy, heat of dilution. So enthalpy of solution, also known as heat of dilution, is the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. That's it. And so it says heat, and that's why this is also known as heat of solution, because we think about this in general taking place at constant pressure. So the change in enthalpy is also equal to the heat transfer. So the enthalpy of solution, or the heat of solution, is the heat given off in the dissolving process. You take a solute and a solvent, like water, for example. It's just sitting there. There's no heat change. Then you pour in the solute, mix it in, and it gets dissolved, and measure the change in temperature of the water to get the heat transfer to the water as a result of strictly the dissolving process. Okay, heat of hydration and lattice energy, what you can think about is the enthalpy of solution. There's two components to this. You need to break up the lattice structure of the solute, and then the hydration process needs to take place. So the broken up pieces need to be hydrated by the water molecules. And so thinking about dissolving ionic compounds, all ionic compounds are soluble. The lattice energy is defined to be the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. That's the lattice energy. And it's not the energy required to separate a mole of solid ionic compound into ions in solution. This is just the breaking up of the lattice structure. So you think about going from solid to gaseous. In the gaseous state, you've got ions on their own all over the place, right? That's the lattice energy. The heat of hydration is the enthalpy change associated with the hydration process. So the ions being surrounded by water molecules. And therefore, the enthalpy of solution is equal to the lattice energy plus the heat of hydration. All right, heat of dilution. Heat of dilution is defined to be the heat change associated with the dilution process. It's just what it sounds like. It's the exact same idea as enthalpy of solution. Whenever that's the enthalpy change or the heat change as a result of the dissolving process. This is the enthalpy change or heat change as a result of the dilution process. Why is the lattice energy of a solid always a positive quantity? Why is the hydration of ions always a negative quantity? All right, so why is the lattice energy of a solid always a positive quantity? Well, think about this. Lattice energy, we just talked about, is the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. That's always going to be an endothermic process. You can think about that intuitively, right? If you think about the inverse of it, so going from a gas to a solid must be an exothermic process then, because right, we talk about if you flip, so if we're going from NaCl solid to NaCl gas, and we put the delta H of this, and then you flip it, it just becomes negative. There's no situation where you have a gaseous compound and then you need to apply heat to it to make it a solid. So the lattice energy of a solid is always going to be endothermic, a positive quantity. Okay, the hydration of ions, why is that always a negative quantity? Well, when you think about it, you're going from the gaseous state, the ions in the gaseous state, to a state where they're hydrated. There's no circumstance where the ions wouldn't be becoming more stable when they go to that hydrated state. That's 100%. You're going from an unstable state to a stable state when you go from gaseous ions to ions hydrated in water. Therefore, heat is released. It's always a negative quantity. The hydration process is always a negative quantity, the hydration of ions. Okay. Consider 2 ionic compounds A and B. A has a larger lattice energy than B. Which of the 2 compounds is more stable? Okay, well, you can think about this intuitively. Since A has a larger lattice energy than B, it's going to take more energy, which you can think about as heat in a constant pressure process, more energy to break it up into gaseous ions because it's more stable. If it's more stable, it's going to be harder to break it up. It's going to take more energy. So A is more stable than B. Mg2+ is a smaller cation than Na+ and also carries more positive charge. Which of the two species has a larger hydration energy? Okay, so when you're thinking about the hydration energy of an ion, first consider the charge. The larger the charge, the larger the hydration energy. Okay, so that's the effective charge. Now, with regards to size, so let's just imagine these two had the same charge. The smaller the ion, if they're the same charge, then the larger the hydration energy, because you can think about the charge density is higher. So this is both smaller and has a higher charge, so the Mg2 plus has the larger hydration energy. Consider the dissolution of an ionic compound such as potassium fluoride in water. Break the process into the following steps: the separation of the cations and anions in the vapor phase and the hydration of the ions in the aqueous medium. Discuss the energy changes associated with each step. How does the heat of solution of Kf depend on the relative magnitudes of these two quantities? On what law is the relationship based? All right, so you've got solid Kf, the dissolution process means you go from solid potassium fluoride to K plus aqueous plus F minus aqueous. All right, now let's go through this indirect path to arrive here. So we have Kf solid, and then we add energy. And this results in K plus gas plus F minus gas. And this is the lattice energy here. Okay, so we can actually we can put U here for lattice energy. Okay? Now, going from here to the hydration, you have K plus gas plus F minus gas, and that results in K plus aqueous plus F minus aqueous, and this gives off energy. What energy does this give off? The heat of hydration. All right, so we've just broken the process up into these separate steps, and we discussed the energy changes associated with each step. Now, how does the heat of solution of Kf, so this is going to have some sort of delta H here, right? And this is going to be called delta H solution. How does this depend on the relative magnitudes of these two energies? So let's add this up here, add these equations up. Okay, so these cancel, and we're left with Kf solid goes to K plus aqueous plus F minus aqueous, this, and then the energies, we can compare these two. So again, we're left with which is this chemical equation, but what's the energy change? It's going to be U plus delta H hydration. That's what delta H solution is. This is the delta H, which is delta H solution. Now, don't get this confused. Whenever you're adding chemical equations like this, the same ionic compounds on both sides, you cancel out because like these are produced here, but then these are consumed here. What you're imagining is you're going from here to here and then from here to here. So this is the net effect. That's why you cancel it out, because this is the net effect of adding the chemical equations. But the energies, you just add up the energies. So it's confusing, but really this U on the left side would mean that the delta energy is positive over here. This on the right side would mean that the delta energy is negative. So you just add them up, right? Technically, it would be like okay, you would say, you'd write this as Kf solid goes to K plus gas plus F minus gas, and then the change in energy, or which would be equal to U, would be a positive because it's endothermic. That's why this is over here. In this case, the change in energy, you could just omit it here and put it off to the side. That would be negative because the energy is given off. It's not absorbed in the reactants. So then you would add, in this case, you would add a positive to a negative, and so it would still be this minus this. I mean, you can think about it that way. It would be this minus this, but I hope that makes sense. you would end up getting positive plus this, but this would be negative because it's on the right side. So yeah, it is kind of like you are subtracting this side from this side. But why is it dangerous to add water to a concentrated acid such as sulfuric acid in a dilution process? Because the heat of dilution is large in this case, right? So we know that there's heats of dilution. And so if you add water, the process of adding water to a concentrated acid like sulfuric acid, that has a high heat of dilution. So it could get dangerously hot quickly.